So, hello everyone. Can you hear me? Okay. Uh, the slides are visible. Just please confirm. Okay, okay, okay. So today I'm going to discuss this assignment 4 of this course. Okay. So let me do first. Okay. So hi everyone. I'm Anush Kumar. I am the TA for this course, and I am here to discuss this assignment 4. Right. So we are already in the week 4 that basically describes about the structures, symmetries, isomerism, and coordination equilibrium, right? So we will discuss the problems related to these uh, basically topics, right? So as usual, I'm showing you the two basic questions. Okay, you have to just give me the answer, and after that I will discuss. First, you should be familiar with what are a stereo isomers. Okay, you have to identify the right options among these four, and in the second one, which ligand is applicable for exhibiting linkage isomerism. Okay, so you already know what is the linkage isomerism. Basically, the ligand which contain more than one donor atom, and it can bind to the central metal atom through any of these atoms. Okay, that will this the ligand present in the complex will exhibit linkage isomerism. Okay, so try to give the answer. After that I will explain in detail. Okay, first A and second D. Okay, right. So if anyone is also willing to give the answer, please type in the chat box. Otherwise, I will proceed for the solutions. Okay. So, yeah. So these are the explanations for both the questions. So stereoisomers are isomers that have the same composition. You can say the same molecular weight. Okay, but that differ in the orientations of those parts in the space. Basically, if your spatial arrangement of atoms is different, okay, so you will get the stereoisomers. Okay, and in the case of coordination complexes, isomer that are formed by exchanging ligands and metal ions are called coordination isomers. Okay, you already studied in detail as taught by the sir in class. Okay, so the explanation for the second one, I have already told what is the linkage isomerism. So, for example, I have taken these two examples, right? So, in the first one, you can see the central metal atom is coordinated with this ligand. That is basically, in first case it is nitroso, and in second one it is nitro. Okay, so in this one, the cobalt oxygen bond is there, right? In the second one it is cobalt nitrogen bond. So this ligand can make the coordination bond through nitrogen or oxygen, right? So among the options here, you can see it can bind through nitrogen or oxygen, and in thiocyanate it can be isothiocyanate, right? It can bind to through sulfur or through nitrogen, right? And in the similarly for this sulfur trioxide anion, right? So you will have this type of structure. Okay, right? So all of these can exhibit the linkage isomerism. Because this sulfur have a lone pair, it can also bind to the metal atom, and these oxygens also, because they are electron rich, right? They can easily donate their charge or their lone pair to the metal atom and can form coordination bond. So in the second one, this is the answer, and first is A, isomers with different spatial arrangements, right? So moving to the next two. So what type of isomerism is present between this and this complex? Okay. So there are four options: geometrical isomerism, right? Coordination sphere isomerism, linkage isomerism, or optical isomerism. Okay. And in the second one, you have to choose the correct statement for chirality. Chirality, it means a superimposable mirror image. Only five coordinated complex, that is, it can be trigonal biplanar or square pyramidal. Okay, yeah. So for the first one, I'm getting the answer B, coordination sphere isomerism, right? And what about the second one? I request all of you to please mute your mic. What about the second one? That is, you have to identify the correct statement regarding chirality. So in the first one, you can see there are different ligand in the coordination sphere, right? In the first complex, they are different, and in the second one, they are also different, right? In this coordination sphere. Okay, so you can get a basic idea from here what isomerism will be there. B and C. Okay, right. I'm waiting for the others also. So moving on to the discussions. So coordination isomers or coordination sphere isomers are two or more coordination compounds in which the composition within the coordination sphere is different, right? So I have taken this complex as example. You can see here, bromide ion is outside the coordination sphere, right? And chloride is inside it. But in other complex, you can see here bromide is in the coordination sphere and chloride is outside the coordination sphere. So these two complexes are uh, so coordination sphere isomerism. In similar scenario, you can see here is the same situation. So what you can see, they will exhibit this coordination sphere isomerism. Okay. Moving to the next one, what is chirality? So basically, chirality, there are some conditions for chirality. Okay, so compounds should not have a plane of symmetry or center of symmetry, right? First one. Second, the structure should be non-superimposable, right? For example, if you take your left and right hand and you just put your left hand on the right one, you will get a non-superimposable mirror image, right? The left hand and the right hand are the mirror images of each other, but if you just put one on one, they will not be superimposed, right? So that is the first condition of for chirality. Second, it should not have any plane of symmetry or center of symmetry. Okay. So chiral molecules have a plane of symmetry. This is an incorrect statement. It is also an incorrect statement. Like this, only five coordinated complexes exhibit chirality. Okay, basically, if I talk about the trigonal bipyramidal case, right? This one. Okay, if you are having these two ligand, two same ligand, so these three ligands, this one, and this one will be in the plane. So if you pass a plane from here, right? So these three ligands will be subtracted or intersect, right? And these two chloride ions are reflected. So you will be getting a plane of symmetry, right? So it basically depends upon the ligand substitution or position of ligands that is basically present in the complex. But in the case of 4 and 6 coordinated complex, they always exhibit chirality, right? So moving to the next two, you have to uh, the type of isomer present in this complex. Okay, they can be cis trans isomer, they can be facial meridional isomer, delta lambda, or none of these. Yeah, yeah. Uh, Regarding chirality, right? Yeah. So for chirality, I have indicated there should be a non-superimposable mirror image, right? It should not have any plane of symmetry, right? And the third one, okay. So I just yeah. So what is the correct statement for chirality? It should be a non-superimposable mirror image. Okay. If you are having a two structure, okay, and they are non clear. Okay. So moving to the next two, you have to identify which type of isomers will be there in this structure of any this complex, right? Okay, just identify. Okay, so before identifying these options, okay, you should be familiar with what is cis trans isomers, facial meridional isomers, delta lambda isomers. Okay, basically this delta lambda isomer is for metal trichelates, right? Chelates, if you are dealing with this ligands, okay, you will be getting this delta lambda isomers as explained in the class. Okay. So for explaining this delta lambda isomer, I am taking the typical example for this. Uh, right, if you have any triskellate, like there are, okay, and this oxygen, and this one, right? So if you are having this type of arrangement, like on from the upper triangle to the below triangle, and then again upper to lower, upper to lower, right? So it will be a delta isomer. Okay, basically these three oxygens uh, in this triangle there is one triskeleton. Okay, basically the ligand having three oxygens. Okay, and similarly for the upper one triangle. Okay, and if I talk about other configurations. Okay, so let me just make it. Okay, similarly if you are having this one arrangement, right, from this one to this one, and this and this. Okay, so that will be our lambda isomer. Okay, so these are delta lambda experiments as sir have already explained in the class. If I talk about the facial meridional isomers, I'll explain in detail in the next slide. Just try to give me the answer for these two questions. After that I'll explain. So basically for this one you should have a triskeleton, but here both the ligands are monodentate. Okay, so this complex will not exhibit delta lambda isomerism. So what about the cistrans and facial meridional isomer? And the second one, what instrument is used for measuring the enantiomeric effect on plane polarized light? Basically you have to measure the optical rotation. So with the help of which instrument you can measure, you have to identify. Let me see. Anybody wants to give the answers? Okay, so in a for metal triskeleton, the two enantiomeric forms are called lambda and delta. Okay, right? And if I talk about facial and meridional isomer, the same ligand are on a common face of a polyhedral complex. Okay, and in the mer isomer, they are on a plane that bisects the polyhedron. Basically, these type of isomerism is exhibited by Ma3B3 type of complexes. Okay, and here you are having, sorry, Ma4B2, right? So if I talk about the facial and meridional isomer, okay, so let me insert here a blank slide. Okay, so in case of Ma3B3 type of complexes, okay, so there are in octahedral complex, right? If this is the metal, okay, and if you are having, okay, 1A and the B is this one. Okay, and similarly you can get a different arrangement. Okay, so if you are having A is here and other A is here and one A is here. Okay, and similarly one B is here, right? And the third possible structure you can get, right? If you are having A and one A is here and one A is here, one B is here, right? So you can see here, if I match these three A, right? This A and this A. So one triangle is forming here, and similarly, if I join the 3B, right? One triangle is forming here. So this type of structure will be called facial isomer. Yeah, fa isomer, right? And in other scenario, if I join these three A, okay, one A is here, right, and other is here. So you are getting a semicircle, right? And if I join these three B's, you are getting other semicircle. Basically, one circle, half circle is perpendicular to the other semicircle, right? And for example, or you can see in this structure also, if this is a half circle, right, and another half circle is here, okay. So here also they are perpendicular to each other. So basically in meridional isomer there are two categories. If you are having A and A, so this one, right, you can see A and B are at 180 degree with respect to each other, so you will be getting a transmer isomers, right? Okay, but in here, if you are getting this type of structure, okay, so A B are 90 degree, so this type of structure will be called cis meridional isomer, right? I think you got my point. So if I talk about the simple cis and trans structure, you can see the typical example of this complex. Okay, so you can see here chloride, the two chloride ligands are 180 degree apart, okay, at 180 degree angle, and here they are at 90 degree. So this will be the cis structure and it will be trans structure. So what will be the right option? It will be the cis trans isomers. Okay, if you got my point, just type yes. Okay, thanks. Moving to the next one. Basically, the polarimeter is an instrument that measures the direction and angles of rotation of plane polarized light. Okay, so it is used for measuring the enantiomeric effect, or you can say the optical rotation. Okay, so ammeter thermometer, ammeter is basically related to the measurement of current. It is related to the temperature, and it is related to the voltage. So This polarimeter will be the right answer. Okay. So the next question is also related to this polarimeter. You have to identify what do you mean by dextrorotatory. You have already read these terms, dextrorotatory and levorotatory. You have to identify, and uh, these are the factors which affect the stability constant. You have to choose. Okay, so just try these problems. I will be waiting for 2 minutes for your answer. This is just basic questions related to your theory part. Okay, try to give the answers. So you know a substance that cannot rotate the plane of polarized light, that will be optically inactive. Okay, and a substance that rotates the plane polarized light in both clockwise and anti-clockwise directions, that will be a mixture, racemic mixture. Okay, and a substance that rotates plane a polarized light in a clockwise direction, that will be dextrorotatory, and in anti-clockwise it will be levorotatory. Okay, and the second one, which factors affect the stability constant. Okay, nature of the ligand, nature of the central metal atom, and chelating effects, both the stability constant is affected by all these three. Okay, so moving to the explanations. Substance or a compound having the property of rotating the plane of polarized light to the right, that is clockwise direction, it is called dextrorotatory. Okay, I have already explained. So, just for I have shown the schematic diagram. If you having any light source, you will be getting a normal light. Okay, so the vibration or will be in all directions because it is a electromagnetic. If you are having a polarizer, it will filter out. Okay, those vibrations will be filter out, which will be parallel to this polarizer. Okay, and if you pass this plane polarized light to your sample, you will be getting a plane polarized light, but the plane of polarization has been rotated. So what you can say this sample is optically active. Either it is rotating the polarized light in the clockwise direction or anti-clockwise direction. Basis on the optical rotation value, it is plus or minus. You can just nominate what is it. It is dextrorotatory, levorotatory. Okay, or if it is optically inactive. And in the second one, stability constant, also called formation or binding constant, is in an equilibrium constant for the formation of complex. Okay, so there are many factors that can affect the stability of the metal complexes: nature of the central metal ion, nature of the ligand, because this the nature of the central metal atom and nature of ligand, that will basically decide the strength of the metal ligand bond. Okay, so how much strong the bond formation is there. Okay, chelating effect is also there, and resonance effect can be there. So all these three factors can affect the stability constant. Okay, so the large kf value, what will indicate in this reaction. Okay, so kf is formation constant. And the second one, on which factors the enthalpic effect depends on. Disorderness is basically related to entropy. Okay, just try to give the answers. Please type in the chat box if you know the answer, please. Or if you have any query, you can also type. Right? Someone is raising the hand. Just type your query, please. Dr. B. Velkanan, please. Okay. Yeah, yeah, please. Hello. Your voice is breaking. Can you just type in the chat box so can I get the clear query? Okay, okay. So you have raised your hand. So I thought that you have a query. Okay. So what will the large formation constant value indicates? Basically, the formation constant tells about the strength of bond forming between the metal and the ligand, right? So if the kf value is large, right? So what does that mean? It means the formation of this complex is very much favored over this complex. And apart from that, the other means is that this complex diethylene triamine, it can easily substitute the ammonia ligand. Okay, right? So the basic idea from the value of kf formation constant, you what you will get, the reaction is favoring in which side. Okay, so the forward reaction is favored here. Okay, and what about the bond strength in the second one? I have already indicated that disorderness is related to entropy. Okay, so there is if there is increase in randomness, okay, or disorderness in any complex, you will be getting the entropic effects. But the enthalpic effect is related to the bond strength. Okay, so if you are having this bond L1 and L2, so the enthalpic values for these two individual bonds will be different. Okay, so if there is a release of higher energy, that is complex is being more stable, so enthalpic effects depend upon the bond strength. So same thing is written here. The formation constant describes the formation of complex ion formed from its central ion and attached ligands. The larger the kf of a complex ion, the more stable. Okay, hence the large size of the formation constant indicates uh, that the majority of the free ligand will combine with the metal atom to form this complex, right? And the second one, enthalpic effect, is a part of the thermodynamic stability constant. Okay, so basically it is a heating effect which also measures how the corresponding enthalpy values are responsible to detect the corresponding formation of the complex. Okay, so thus enthalpy values depend on the bond strength, whereas the other part of thermodynamic stability constant, entropic effects, is depend on the disorderness. Okay, so what will be the right option? This one. Clear? So moving to the next two, how many structures are possible for this type of complex, this particular complex? Okay, examine cobalt chloride, and how many isomers are possible for this. This is basically cisplatin. Oh, yeah. It is a anti-cancer drug only in the cis form. So that's why its name is famous as cisplatin. In trans form, it doesn't work as anti-cancer drug. Okay, so if you are having two isomers, they will impart different properties. Okay, let me see if I am getting any answer from your side. Else I will explain. Okay, so two. Okay, right. And what about the first one? Any guess? Okay, so basically, first I'll discuss the second one. So you will be getting these two structure. In first one, you are getting the cis chloride ions, and in other one there are trons, right? It is basically a square planar complex. So you will be getting the two structural isomers. Okay, and what about the second one? Okay, so basically in the second one, in the first one, you will be dealing with the coordination sphere isomerism, right? So you can see if this is the structure, okay, here the chloride ions are outside the coordination sphere, right? So in Werner theory, you can see these chloride ions are shown by the dash bond. Basically, what it is indicating, it is showing the primary valency, okay, and these bonds are related to the secondary valencies, okay. And the other possible structure, what it can be, one chloride ion can be inside the coordination sphere and two remain outside the coordination sphere, right? And similarly, all the three ligands can be present inside the coordination sphere. Okay, so you can see here this chloride is connected to cobalt through dash bond and this dark bond also, because what it basically indicating, okay, so it is just arriving into the inside the coordination sphere. Okay, so how many structures are possible? One, two, and three, and four. Okay, So four structures are possible for this type of complex, right? The next one, this complex, there is any complex, it will react with the NaNO2 in presence of concentration HCl to form concentrated HCl to form a compound which exists in both yellow and red form. Okay. Yeah, please. Yeah. No, 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 no. This chloride is primary because when you will synthesize this one, what will be the precursor? You will start from this one. Yeah, inner and outer. Outer. Yeah, yeah, yeah. Because what you are just doing, you are interacting with this one, and you will be getting these ligands substituted by this one. Okay. So, but in previous, yeah. Now, just you confirm, please. Okay. So, just try these two. And apart from that, in you are getting a basic idea inside the coordination of a sphere. You will be getting the basic idea about coordination number, right? But outside the coordination sphere, you will be getting the idea about what is the oxidation state, right? Okay, so these two information you can get. Okay. Yeah, just try these two. Basically, this ligand, that is NO2, that will replace with the water molecule, and you already know that NO2 can exhibit two tautomeric forms. It can be exist as this one, or it can be exist as this one. Okay. So what is the product that will be formed? It can have a cobalt nitrogen bond, or it can have a cobalt oxygen bond. On the basis of these bonds, you are getting a different color, yellow and red. So what isomerism is, just basically I can expect, it is basically a linkage isomerism, right? Okay. So what about the second one? You can see in the coordination sphere, here you are getting a different metal atom, and here it is a different metal. Okay. Basically here chromium is outside the coordination sphere, and here iron is outside. Okay. So you will be getting the coordination sphere mechanism, isomerism is there. Okay. So basically this is a reaction. I have already explained this. Water molecule will be replaced by this one, NO2 ligand. Okay. Or it can exist as this one also, right? So the next two, chromium bonded thiocyanato complex is bonded by nitrogen donor of NCS, because this question is basically related to the hard acid hard soft acid base principle. That basically states that hard site or hard. Yeah, yeah, yeah. I have already explained. Okay, so in this, you can see inside the coordination sphere. Okay, so there are two different metal atoms. Okay, here iron is outside, here chromium is outside. So they will exhibit coordination sphere isomerism basically. Okay, right. So try these two. Just try to solve. I think you are already familiar about HSAB principle, hard, soft, acid, base. Okay, so what it states, hard acid will make a strong bond with hard base. Okay, hard Lewis base, you can say. Okay, so hard acid, what it will be? Hard acid that will, for example, in this one, it is plus 3. So it is highly electron deficient. Okay, it has a high charge. Okay, other conditions for this hard acid, that the entity should be smaller in size. Same goes for the hard base. Okay, it should have a high electron density and small size. Okay, and the electron cloud of which is not easily polarizable. Okay, so in this case, chromium 3 is also a hard metal ion, and N is also hard. Okay, what about the other one? That is the instability constant for these two complexes are given 1.3 in 10 raised to minus 3 and 8 into 10 raised to minus 21 respectively. If C1 and C2 be the concentration of this ion, silver ion, in equimolar solutions of these two complexes, then what will be the relation between C1 and C2? Okay, so basically instability constant is related to the dissociation. Okay, so from this information, what you can get. Okay, if I am having a greater value k1 and k2. Okay, if k1 is the instability, k is the instability constants. Okay, and if I talk about the stability constants, Okay, so they will be like that. Okay, so the concentration of silver ion in equimolar solution for this complex, what will be the concentration? You can see easily, if this complex is unstable, okay, so the more silver ions will be there in the case of this first one. Okay, if I talk about this complex, there will be less amount of free silver ions because the silver ions will be forming the complexes, right? And the stability constant will be higher for this one. Okay, so the right answer will be this one. Getting my point? Okay, okay, okay. So you can see there are two values given here. One is this, second is this. So you can see this value is higher, 1.3 into 10 is to minus 3 as compared to this one. Okay, so if I am talking about instability constant will be higher for this one as compared to this one. Okay, so what it will be basically telling about, uh, simply if I talk about this Az plus forming this complex, right? So if I talk about the stability constant, I'm not talking about instability constant. I'm talking about stability constant, that is basically relation related to the association. Okay, and another equation that is formally I am writing here, that is AzNO2. Okay, so instability constant for this one is having a higher values as compared to this one, right? So vice versa, if I am talking about the stability constant, the trend will be like this. Understand? You're getting my point? Yeah. So what it will be? This complex is unstable. That means it will be basically dissociating in the solutions because it is having a higher value of instability constant. It will be easily dissociating and it will release this ammonium silver ions. Yeah. So concentration of Ag plus will be higher in this case as compared to this one. Clear? Ah. So the next one is also related to this concept. Addition of potassium iodide to a solution of this precipitates silver iodide, but no precipitate formed when Ki is added to the solution of this of same molar concentration as the amine complex. If the instability constants, that is basically related to dissociation, not association. Okay. So if the instability constants of the two complexes be K1 and K2 respectively, what will be the trend? Here also you can apply the same concept and get the answer. Okay. So thank you very much for attending this session. This was all about this assignment 4. Okay. If you are having any query, please type. Okay, just are you getting the YouTube links and the PPTs as slides on routine basis? Yeah. Actually, your voice is very low. Please just type in the chat box. I will read. No problem. Okay, okay. I'm just give me. So you are asking about what is the coordination number of bicap trigonal prismatic, right? I think I have explained in the last class. The coordination number is 8. I have, I think I have taken the example in the earlier class. Okay, okay. So thank you for attending this session. I am just now closing the meeting. Thank you.